Let us now discuss about life cycle cost. It is called LCC for short. It's an acronym. With an example, we will also see how we will go about doing the life cycle costing analysis. What are the various components of life cycle cost? First, we need to know about capital cost. We need to know about a replacement cost. So the capital cost is the initial investment that you would put at point 0 time 0, which is now today. Replacement cost are actually after some years down the line, some of the subsystems which have lesser life than the overall lifespan of the system needs to be replaced. So they will have to be reflected back to the present for comparison, for adding and comparison. Then there is the maintenance cost. You will have the annual maintenance cost coming to the picture, or maintenance cost in general. Sometimes you will have energy cost, and then the scrap value or the scrap cost. Scrap cost is actually the salvage value at the end of the life. If there is any amount, any cost, any price that you can recover from it, that is subtracted. These are all investments from your side. Scrap cost is actually coming back to you, whatever left, whatever is remaining. So let us give some symbols. Capital cost we'll call K, replacement cost as R, maintenance cost as M, energy cost as E, and scrap cost as S. Energy cost and scrap cost need not come always. Sometimes you will not have any scrap cost, and sometimes you will not have energy cost in particular system. It will be insignificant. But most of the time you will definitely have capital cost, replacement cost, and maintenance cost in most of the renewable energy type of systems. Now LCC, life cycle cost, is given by K, capital cost, plus R, replacement cost, plus M, maintenance cost, plus E, energy cost, minus scrap value. So this is the life cycle cost thing. You will generally define a period of life. So 15 years life, do the analysis for 15 years, 20 years life of the system, entire system, perform a life cycle costing. So generally that is how it goes. We will try to understand this by working out a simple example. Let us consider an example. Calculate life cycle cost for a PV based pumping system which has the following data. Now what is the data? Let me tabulate that. So what are the subsystems? I will list that down. Then in one column I will give cost, and another column I will give life in years. So in the PV based pumping subsystem, one of the main items would be PV array plus balance of systems. Now I will put an approximate value, rupees 80 per watt peak is the cost for the PV array and balance of systems, and the life is 15 years. Motor plus motor pump set, it is around approximately rupees 5 per peak watt, 7.5 years. Miscellaneous for transport and such, I will put ₹3 rupees per peak watt. Then piping costs, ₹100 per meter, and the pipe have a lifespan of 5 years. Then cost of well, the normal well, rupees 300 per meter, and then no life. So I will just put some representative costs. Probably at the time of calculating, you will have to go to the market, check, and then put the actual costs to get a more realistic value. Anyway, here we want to study the concept. I will just put approximate values of the costs. So this is the data that is available to you. Let us specify the system. So PV array ratings is 500 watt peak. The pipe length is 30 meters. The well depth, the depth to which the well is dug out, is 10 meters. The period of interest, the period for which the analysis has to be performed, is 15 years. Means 15 years lifespan of the entire PV based pumping system. Let us take interest as 10%. 10% is on the higher side, but doesn't matter, easy for calculation. Annual maintenance charges, there is AMC. Annual maintenance charges for the entire system is rupees 1000 every year for the total 15 years lifespan of the system. So now let me draw the timeline to understand what this whole system is. This is time 0, and that is where all the capital investment is made. Now I'm going to split the entire timeline into 3 intervals, 5 years, 5 years, 5 years, so that you get a total of 15 years entire lifespan. So I will mark that 5 years, 5 years, 5 years. Right at the center here, 7.5 years from here. You see that the lifespan of the motor plus pump is 7.5 years, which means at the end of 7.5 years, you have to make a preventive replacement for the system to function. Pipes, 5 years. At the end of every 5 years, you have to make a replacement for the pipe. So we will do that. So let us note down, at 7.5 years, we have to make one replacement for the motor plus pump. Then at the end of the first 5 years, you have to make one replacement of the pipe set. At the end of 10 years, second 5 years, pipe replacement again. And then you see the end of the lifespan, so you don't need to make any further replacement. So 2 pipe replacements and 1 motor pump set replacement. Next, I am marking tick marks for every year. So now you have 1, 2, 3, 4, 5, so on up to year 15. Now this is for the annual maintenance. We have an AMC of 1000 rupees that we need to give every year. We need to give 1000 rupees here at the end of the 3rd year, 4th year, 5th year, so on, the end of the 14th year and end of the 15th year. So like that, AMC has to be given every year. So this is geometric progression. We know how to solve that. We will do that at that point in time. So now we need to calculate what is the capital cost, what are the replacement costs in red, what are the AMC costs, what we have written in green. So let us do that exercise. So first let us calculate the capital cost, K. So RA cost, rupees 80 per peak watt into 500 watt peak is rupees 40,000. Then motor pump cost, rupees 5 per peak watt into 500 watt peak, which is rupees 2,500. Then we have the miscellaneous cost. We had put rupees 3 per peak watt. Into 500 watt peak. This is rupees 1500. The pipe cost rupees 100 per meter into 30 meters, which is rupees 3000. Then the cost of the well is rupees 300 per meter into 10 meter. This is rupees 3000. So when you add up all these things, you get K, the capital cost, which is rupees 50,000. Next, let us calculate the replacement cost, R. We saw that we need to replace a motor pump set at the end of 7.5 years, one replacement in the entire lifespan, R1 I will call it, 2,500. This is the motor pump cost. As there is no inflation, we have not given an inflation value. We should assume inflation rate F is equal to 0. So 2,500 into 1 by 1 plus I to the power of 7.5 will be the present worth. So whatever 2,500 rupees you are going to put at 7.5th year, present worth, reflect it to the present, and you will get rupees 1223.2. Then pipes replacement, we need to do 2 replacement, one at the 5th year and the other in the 10th year. So we know that the pipe cost is 3,000 rupees. So let us 3,000 1 plus I to the power of 5. So the 5th year replacement reflected back present worth will be 3,000 by this much, plus 3,000 by 1 plus I to the power of 10. So the 10th year present worth reflected back to the present is this value. You add both of them, 1862.76 plus 1156.63 comes to is 3019.4. So when you add all the replacements, you will get R is equal to rupees 4242.6. So next we will calculate the maintenance. Maintenance cost M. So maintenance, we saw that the annual maintenance we are paying 1,000 rupees every year. It is like the equal installments payment every year. So M is equal to AMC into 1 by I, 1 minus 1 by 1 plus I to the power of n, which is the present worth factor. So which is 1000 into present worth factor. If you substitute for I.1, you will get 7.6 and n as 15. So 15 installments will give you, distributed over 15 years, will give you rupees 7,606. Next, LCC, which is K plus R plus M, capital cost plus replacement cost plus maintenance cost, which is 50,000 plus 4242.6 plus 7,606, which will turn out to be rupees 61,848.67 rupees. So this is the life cycle cost, total life cycle cost taking 15 years lifespan. Now it will be interesting for us to distribute it over the entire 15 years in an annual way. What is the equated annual installment that someone would pay for a present worth value of this? So let us use the timeline T. Now at time 0, then year 1, year 2, so on. 1, 2, so on to 15, year 15. That is our lifespan. Now at that time 0, we have the LCC value of 61,848.67 rupees. That is the worth of the entire system as of now, as of today. That is the life cycle cost. Taking into account all replacement, maintenance, everything has been reflected back into the present. Now this value, can we distribute it as equated yearly annual installments for the next 15 years? That will give you what is supposed to have been the payment, annual payment, equal annual payments for this particular system, which could give us a reference or a benchmark. So we would like to have ALCC, annual LCC value, so which is at the end of every year, annual ALCC value. Something like equivalent annual payments for this particular system in operation. So this we know how to do. LCC is equal to the present worth is equal to annual equal cost. This is a geometric progression into the present worth factor. And we know the present worth factor, how to calculate. Therefore, ALCC, the annual LCC is equal to ALCC, which is equal to LCC divided by present worth factor. And LCC is 61848.67 divided by 7.606, which will give you rupees 8,131.5. So this is the annual LCC. What it basically means that this value of 61848 total system cost as of today, all reflected to the present time frame, is equal to saying that every year for the next 15 years I pay 8131.5 every year, 8131.5, 8131.5, 8131.5 till the end of the 15th year. This is equal to saying that this is the equated annual installments for a 15-year period. So this would give a nice benchmark for comparing other similar systems. I have here a small script file. I will share this with you for working out example 1 that we just discussed. Calculate the LCC for a PV based pumping system having the following data. So we discussed, I have just classified the script file into subsystem data part, where I have listed down the data, the cost of the PV plus array of the pump, the life of the PV array, and all those data which we just tabulated. Then I have the system specification, which states the array rating of 500 watts, pipe length, well depth, the number of years of interest, and the interest rate of interest, AMC, all these things are specified. And then I have the life cycle costing calculations. First you calculate the K, which is the capital cost. So I have calculated here the array cost, the motor pump cost, miscellaneous cost, pipe cost, well cost, and then you add up all these costs to obtain the capital K. Then you calculate the replacement costs. Recall that we had one motor pump set replacement at the end of 7.5 years, and we needed to replace the pipes one set first at the end of 5 years and the other at the end of 10 years. That is calculated the present worth. You add up the motor pump set replacement cost and the pipe replacement cost, the present worth of both of them, and obtain R, the total replacement cost. Then you calculate M, the maintenance, calculate the present worth factor, and calculate the maintenance present worth, which is AMC, the annual charges that you are paying every year, into the present worth factor. And then finally calculate LCC, K plus R plus M, and distribute it equally over all the 15 years to get ALCC, the annual LCC. Then I have the display part, display the various calculations. So this will perform the calculations for that example and give you the results. Here I have Octave environment open, run the example ex01. I have stored it as ex01.m. I can run that. I'll share this script file with you. So after you run, the calculations are displayed, and observe that all these values which we had calculated is what will be displayed, and then you can take conclusions on that. I will leave it to you to try out for different system data and different system specifications along these lines. You can modify this script file to suit your needs.